Alright, in this video we'd like to do some derivations of the three uniform acceleration equations. These equations are very important and we use them to solve lots of problems in physics, and so I'd like to take a little bit of time and just kind of look at how we derive them. The first equation we don't really need to derive if we just remember. The first equation is what we call the car commercial equation. The acceleration is the change in velocity. We have Vf minus Vi all over t, change in velocity over time. And these are uniform acceleration equations. I mean, the acceleration is always constant, so something is always going faster and faster and faster at the same rate, or going slower and slower and slower at the same rate. Another way to write this equation, the way that a lot of times we write it, is Vf equals At plus Vi. And the reason we write that way is because it's like y equals mx plus b form of the equation. So this is equation number one, very important, and we'll use that a lot for various things. And you'll notice that in this equation there are four variables. In all three of our equations, we're going to have acceleration, and we're going to have initial velocity. So those are going to be in all three of them. So we're going to look at the other variables that we have. In this equation here, we have final velocity, and we have time. So that's important, and there's one other variable that will find useful to know, and that is displacement, or d. And you'll notice that displacement is not in this equation. So if you get a problem that does not have a displacement in it, chances are you're probably using this equation. You're not going to get every single variable every single time. So you're going to usually get two variables. You'll either get final velocity and time, or you'll get time and displacement, or you'll get displacement and final velocity. That's why we need three equations. So we're starting with this first equation, which is in a form of final velocity and time, and we want to derive from this a new equation that will be it'll always have A in it, it'll always have acceleration, it'll always have initial velocity, but we're going to have a new equation here that will be in terms of displacement and time. So I'm not going to have a final velocity in my equation. So somehow I need to get, in this equation here, I need to kind of get rid of the final velocity. So how are we going to do that? Okay. What we can do, let's change colors here so we can see the derivation here. We can think of average velocity, because there's two equations we could use to calculate average velocity if something is uniformly accelerating, and you might be able to figure both of them out. It's pretty easy. If something is uniformly accelerating, it's just going faster and faster and faster at a constant rate. If you want to figure out the uniform or the average velocity for an entire trip, there's two ways that you could do it. You could say that average velocity would equal the displacement, the total displacement, d, over time. How far it was displaced over a certain amount of time, and that would give you an average velocity. It wouldn't give you an instantaneous velocity at any point on the trip. It would just say that the average velocity was the total distance that you traveled, the displacement you traveled, over the amount of time. So that's one equation we could use for average velocity. Another one we could use is probably even easier. That's pretty bad. Let's see if I can do this better. Average velocity. Another equation we could use for average velocity would be if we're just constantly accelerating, we could add the initial and the final velocity and just average them. So we could take the final velocity plus the starting velocity and divide them by 2. And so we'd have an average velocity there. So both of these would be average velocities, ways to calculate average velocities for a uniformly accelerating object. An object's going faster and faster at a regular rate or slower and slower at a regular rate. And we don't want average velocity in our equation, so you might figure out what we're going to do here. We're going to set these two to be equal. So I can have d over t equals vf plus vi all over 2. Okay? And we said then this first equation here was in terms of final velocity and time. In this equation, we're still going to have acceleration and initial velocity. Right now we still have initial velocity here. We don't have an acceleration here. But we do want this one to be in terms of t, which is in there, and d, which now we have in there also. The problem is we still have a final velocity in there. We don't want that one in there. And so what we can do is we have an equation for final velocity right here. So if we take this equation and sub it in for my final velocity right there, I will be able to get rid of my final velocity. So if I do that, I'm going to have d over t equals, and then I'm going to put in at plus vi in for my vf. So I'm going to have at plus vi plus vi all over 2. Okay, so now what can I do? Well, I could cross and multiply here. So I could have 2d equals, let's see, I'm going to take t times this whole top part, so I'll have at squared plus vi t plus vi t. Okay, so now what I want to do is I want to let's see, at squared plus, yeah, okay. So I can, I have two terms that are exactly the same here, so I could do 2d equals a t squared plus 2 vi t. And now I'm going to divide everything by 2, so I will have d equals, we'll call that 1/2 at squared, because that's kind of usually how we write it, plus vi t. d equals 1/2 at squared plus vit. And so this right here is our second uniform acceleration equation, and you'll notice that this one is in terms of d and t. It does not have a final velocity in it. It still has an acceleration and it still has an initial velocity in it, but it's in terms of displacement and time. So if I was given a problem that did not have any final velocities in it, then maybe this is the equation that I'm probably going to use. It has a displacement and it has a time in it. So you have to do an inventory of your problem and figure out exactly what is given, and then you'll be able to know which equation you might want to use. So here is equation number 2, very important equation. Equation number 2. And we had, up here, we had equation number 1. Very important equation. And now what we want to do is we want to do a third derivation, and we want to figure out how to get an equation that still has a and t in it, but has, what's our last thing we need? We need final velocity, and we need distance. So we need an equation that does not have the time in it. It does not have the time in it. So we're going to start with this equation again, d, our second equation. We're going to start with that. D equals, and maybe I'll rearrange this, VIT, we'll do that part first, VIT plus 1/2 AT squared, which is a lot of times how I write it, so it doesn't matter which way you can write this. So if we can figure out a way to get rid of the t, we'll be good. Well, we can come over here to, this is the second equation we're going to start with, but we can also use our first equation, because we can take this first equation here and rearrange it. So time would equal final velocity minus initial velocity over a. So if we put this big thing in for t, it's going to be really ugly, but that's what we're going to do. And so we can sub this in for our t and work on a derivation here of our algebra to try to get to an equation that has distant displacement and final velocity, but no time in it. So I'm going to have d, displacement. Let's see if I can do this neat. I'll try to do as neat as I can. I'm not very good at this yet. Displacement equals initial velocity times time. Okay, so what's time going to be? It's going to be big and ugly. Vf minus Vi all over A plus 1/2 A times time squared. Ugh, okay, so that'd be Vf minus Vi all over A, and we're going to square that. Okay, so let's keep on working here. We're going to get d, I better come over here a little bit more, d equals, we can distribute this vi through here, so we're going to get vi vf minus vi squared, right, all over a plus, and 1/2 a we'll write as a over 2 times, okay, so we're going to try to square this whole thing. So on the top we're going to get vf squared minus 2vi vf plus vi squared. And this is getting to look very bad. I'm really apologize about this. I'm just really bad at this. All over a squared. Okay, so that's a minus 2vi vf in there, and I'll try to clean that up this next time around maybe. So I'll move over a little bit. D equals, and we'll have vi vf minus vi squared all over a plus, okay, we're going to try to multiply this through here. If on the bottom here, I'm going to have an a and an a squared cancel out, and I have a 2 on the bottom, so I'm going to have 2a on the bottom, 2a, and on the top I'm going to have this top part, I'll have vf squared minus 2vi vf plus vi squared. Okay, good. So now I could take 2a times this whole thing. So I'll end up with 2ad equals, and so what do I have here? If I do that, I'm going to have, if I multiply by 2a, the a's will cancel out, but I'm going to have a 2 on the top. So 2vi vf minus 2vi squared. And what am I going to have over here? Well, if I take it all times 2a, I'm just going to have what I have on the top, vf squared minus 2vi vf plus vi squared. Okay, so now what do I have? I'm going to have some interesting things happen, because I can have, right here I have 2vi vf minus 2vi vf, so that part there and that part there can cancel out. Here I'm going to have a minus 2vi squared plus vi squared, so that's going to be a minus vi squared. So I'll do a nice new color, 2ad equals, I'm going to have a vf squared, vf squared, and then a minus vi squared. So this looks a little nicer. We're simplifying it here. And a lot of times we write it in terms of VF squared. So I'm going to have VF squared equals VI squared plus 2AD. And you'll notice here now we still have A in this equation. We still have initial velocity. As I said, we're going to have A, acceleration, initial velocity, in every single one of these equations. But in this time, we're going to have, it's in terms of displacement and final velocity. So we have three equations for whatever variables we get. We have one up here in terms of final velocity and time. We have one here in terms of displacement and time. And then the third one we have is in terms of displacement and final velocity. So this equation here, you might recognize this because there's another way to derive this from the conservation of energy, and which you have done and might be able to do and might recognize. So here's our three derivations that we have here on how to use uniform acceleration equations. So now basically this entire unit is going to be problems of motion, of different things moving, and you're going to use one of these three or maybe a couple of these in conjunction with each other to determine various answers. So these three equations are really good equations to commit to memory or to put on your Herman's Helping Hand and practice them a lot. So hopefully you understood those derivations, and it'd be nice if you could actually do those derivations yourself. So you might want to start with this one and then figure out average velocities and try to work on the next one and go from there to the final equation so you can always derive them yourself. So hope you understood that all.